Because intuition in infinite series is hard to come by, I found this little rule of thumb to be useful. So let me tell you a quick story, shall we say, about how I see the topic of infinite series. I like to think of it as a race. And it's a race between the terms of a series. So let's say that, maybe over here I have 1 over the square root of n or something like that. And maybe over here I have 1 over 2 to the n. And it's a race between the terms of the series, the terms of a sequence, to their finish line. And what is the finish line of a sequence? If that series has a chance at converging, where are the terms going? Well, not just that. The terms of the sequence have got to be going to 0 in order that my infinite series has any chance at converging. So I think of 0 as being like the finish line. And if there's any chance of an infinite series converging, its terms had better be running toward that finish line of 0. So 1 over the square root of n, for example, and running from 1 to infinity. 1 over 2 to the n, and running from 1 to infinity. Now, we already happen to know whether or not these two example series converge or diverge. Let's start with the one on the bottom. Summation of 1 over 2 to the n. Converge or diverge? This one converged, and how do we know? What kind of a series was this? Well, yeah, we can't let p equal n, right? P for a polynomial series is a constant. Well, p doesn't equal 1 either, because where is the n in my term here?
Oh, p equals -1, which is less than...
This series is not a polynomial series at all. It's a geometric series from yesterday. So instead of having a p, instead of having a degree, it has an r, a common ratio. And what is that common ratio? It's 1/2. And what is important about the common ratio of a geometric series to decide whether or not it converges? It has to be less than 1, and it has to be bigger than -1. There we go. So it's a geometric series. Its common ratio is 1/2, which is between -1 and 1, and therefore that geometric series converges. In fact, we can also say what it converges to with our formula, first term over 1 minus the ratio. So if we cared, we could say that this converges to the first term, which is 1/2, over 1 minus the ratio, which is 1/2, is equal to 1. But maybe we don't care right now. Anyway, the point is that the reason that a series converges, the excuse, its terms are not just going to 0, that's necessary, but they're going to 0 quickly enough. The terms are getting small enough, quickly enough, that they actually add up to something finite. So in other words, these terms are going to 0 quickly, quick enough. On the other hand, we just looked a moment ago at the example summation of 1 over the square root of n. What did we decide about that series? This one is a polynomial series with p equals 1/2. And what is important about that exponent that tells us whether or not it converges or diverges from our classification? It diverges because this exponent is less than 1. So in other words, even though the terms of that series were still racing towards 0, they weren't getting there quickly enough. Too slow. So in the famous race between the tortoise and the hare, here the tortoise won. I guess it always wins in the nursery rhyme. So in order to converge, the terms of a series, the sequence of terms, have to be going to 0 quickly enough. They need to be getting small enough, fast enough, in order that they can add up to something that's finite. And at this point, what we have is sort of two different classifications. We have geometric series, which we could also call exponential. Maybe I'll just write the word geometric up there to connect it to what we have down below. So we have geometric series. And we know that any geometric series, as long as its ratio is less than 1 and bigger than minus 1, that those geometric series are going to be convergent. We also have polynomial series of varying orders, right? Varying values of p. In addition to 1 over n, we might also have 1 over n squared, 1 over n cubed. And on the other side, we might have 1 over the square root of n, 1 over the cube root of n, etc., etc. And today, using the integral test, we came up with a classification of which ones of those polynomial series converge and which ones don't. So on this little thermometer, what I'll do is I'll indicate where the convergent series belong and where the divergent series belong. So starting with 1 over n cubed, converge or diverge? Converge, because their p is equal to 3, and 3 is bigger than 1. 1 over n squared converges. And as we get closer to 1 over n, all of the ones on the right-hand side of this line are convergent. But then what about 1 over n? Right. That series diverges, and so therefore does 1 over the square root of n, 1 over the cube root of n, and everything to the left of it. So there's this dividing line here that divides those series whose terms approach 0 quickly enough that their series converge, that they add up to something finite. That includes all of the polynomial series with exponents bigger than 1. It also includes all of the geometric series as long as their terms go to 0. And their terms go to 0 precisely when the ratio is between plus 1 and minus 1. So for the sake of this little chart, we're going to say that all the geometric series converge. But then as soon as we cross the line, and that line is somewhere right around 1 over n, where exactly it is a much deeper question. But we definitely know that once we reach 1 over n and get to the left of that line, now everything which is slower than 1 over n, in other words, those sequences which approach 0 more slowly than 1 over n does, well, all of them must diverge as well, because they're running slower than the hare in this race. So the point of comparing one series to another is to take something that's complicated and relate it to something that's simple. Relate it to something which we already have pinpointed its location on what I call the order thermometer up here at the top. So when I say order, what I mean is the speed at which a sequence approaches its limit. So how fast the sequence of terms approaches 0. So when I say the word order, that's what I mean. And I don't think that's a word that's necessarily used in your textbook. So this is something a little bit off the page here. But the point is that if we know how quickly a sequence of terms approaches 0, and we can compare it to how quickly maybe one of these two sequences of terms approaches 0, then we should be able to compare one sequence to another and make a conclusion on whether or not it converges or diverges based on that comparison. So let's just start with a simple example. So let's clear out some space here. Yeah. So now I have a series which is not exactly a polynomial series, and it's not exactly a geometric series, right? It doesn't exactly have one of the forms that we already know. And so what I'd like to do is to make a comparison between this series that we don't know what it does and another series which we do know what it does in order to determine whether or not this is a convergent series. So based on what this series looks like, what would be a good example of something I could compare it to? What does it basically look like? How about 1 over 2 to the n? After all, the only difference between these two is this little plus 1 in the denominator. Now, this little approximately equal to sign here in the middle is not really what we want, right? We want a better way to compare one of these series to the other. And I'd like to know, because I happen to know that 1 over 2 to the n gets to 0 quickly enough to converge, because what kind of a series is it again? It's a geometric series. And because it's geometric, and its ratio is between plus and minus 1, its ratio is 1/2, that places it on the order thermometer somewhere in here. So we know that one converges. And then the question is, how does our series compare to this series? And there are two different ways we can answer that question. The first one is by directly making a term-by-term comparison. This is called in the book a direct comparison. Namely, what we would be allowed to do in that case is to say, is there a way that we can directly compare the value of 1 over 2 to the n plus 1 with the value of 1 over 2 to the n? Which of these two fractions is bigger? 1 over 2 to the n is bigger than 1 over 2 to the n plus 1. How come?
Because the bottom is bigger than the bottom of the second left.
Right. So remember, in a fraction, the denominator is bizarro world. If I make the denominator of a fraction bigger, I have made the fraction smaller.
I meant that one's bigger.
Right. So 2 to the n plus 1, because the denominator on the left side is bigger than the denominator on the right side, that makes the fraction on the left smaller than the fraction on the right. So there's what we call a direct comparison between these two series, really between these two sequences. But because I have a direct comparison between the sequences, that comparison also holds for the partial sums of these sequences. So if I were to put a summation sign out in front with n equals 1 to capital N, that this would still hold. And then because limits are monotonic, I can take the limit as n goes to infinity and conclude that the infinite series also compare in the same way. And so my infinite series is less than the infinite series 1 over 2 to the n going from 1 to infinity. And because we know that the summation of 1 over 2 to the n converges, that makes the value over here finite. And so my interesting series is less than something which is finite. And if it's less than something which is finite, that must mean that it too is finite. So what have we proven about this series using a direct comparison? We've proven that this series converges, because a direct comparison between its terms and the terms of the geometric convergent series, 1 over 2 to the n, shows that our series is less than that convergent series, and therefore must be convergent. That's a direct comparison. And direct comparisons are fiddly, because they require you to actually come up with an inequality to show that for all values of n, or at least for all values of n past a certain point, that either one series' terms are always less than the others, or one series' terms are always bigger than the others. It's not my favorite method to compare two series. My favorite method is the one that's kind of shown up here on the screen. My favorite method is to haul in a referee to decide who's winning this race. The race between the terms of 1 over 2 to the n plus 1 and the terms of 1 over 2 to the n. And it just so turns out that that referee has a name. And his name is Monsieur L'Hôpital. So you learned about L'Hôpital's rule in Calc 1 as a means by which to compute the limit of a quotient, or a limit of a product, or really the limit of an indeterminate form. Well, it turns out that what was really happening behind the scenes of L'Hôpital's rule is the same thing that's happening here. Because the value of the limit of a quotient, if that limit is indeterminate, depends on how quickly the numerator and the denominator are approaching their own limits. So here's the idea. What L'Hôpital can do for us is it can compare for us the speeds of these two sequences of terms approaching their limit. And the way it works is that we'll just forget about the series for a minute and just deal with the sequence of terms. That if I divide one of these sequences by the other, let's say I do this, and then I take the limit of this quotient as n approaches infinity, then what I should get, n approaches infinity, well, at least in the beginning, what do I end up with here? If n approaches infinity, what's happening to 1 over 2 to the n? It's going to 0. And what's happening to 1 over 2 to the n plus 1? Also going to 0. That's what makes this an indeterminate form, right? Because both the tortoise and the hare are going toward the same finish line. They're both going towards 0. Which one of them wins depends on how quickly they're running. And the value of this limit depends on whether the numerator gets to 0 faster or whether the denominator gets to 0 faster. And L'Hopital's rule is a way to determine which of those two is happening. So how does L'Hopital's rule work?
The ratio test?
Close, but not yet. I mean, we're taking a ratio here.
Find out which one's increasing fastest.
Right. Well, that's what the answer is going to be, ultimately. Is it's going to tell us which one is getting to 0 faster. So let's suppose I want to evaluate this limit, 1 over 2 to the n plus 1, divided by 1 over 2 to the n, as n goes to infinity. Well, it's probably a better idea to simplify this limit, just getting rid of the compound fraction. If I get rid of the compound fraction, I end up upstairs with 2 to the n, and I end up downstairs with 2 to the n plus 1. Now, instead of 0 over 0, I have an indeterminate form, infinity over infinity, as n goes to infinity. But again, we still don't know what the value of this limit is. So what does L'Hopital's rule tell us to do for this indeterminate form? Take the derivative on the top and the bottom. So now he comes in with his little whistle or whatever. That's a terrible looking whistle. Whatever, he's holding a whistle in his hand. And he comes in and tells you to take the derivative of the numerator and the derivative of the denominator. Well, what's the derivative of 2 to the n? Anyone got this one off the top of their head?
I would say n2 n minus 1.
If the exponent were a constant, I would agree with you, but the exponent is our variable. And so this is an exponential function, which means its derivative follows that pattern. 2 to the n times the natural log of 2. If it were just e to the n, its derivative would be e to the n. But it is a scaled version of that. So we get this factor of ln2 that comes out. What's the derivative of the denominator going to be based on that information? Same thing, but the plus 1 is what's going to happen to it when we take its derivative? It's gone. And this still looks like an indeterminate form as n goes to infinity, but what actually happens in my fraction?
They cancel out.
They cancel out. And it turns out that the limit is equal to 1. So let me just compactify what we had here. We started with the ratio of, on the one hand, the terms of the sequence whose series we were interested in finding out about, 1 over 2 to the n plus 1. And in the denominator, we had 1 over 2 to the n. And we found out that as n goes to infinity, the limit of that ratio is actually equal to 1. So what does that tell us? Yes, but let's be careful about that. So I want to explain why this means something, why this tells us something about the race in between these two sequences of terms.
Because they're equal to each other.
It tells us that the speed at which they approach 0 is equal, that they approach 0 with equal order or equal speed as they go to 0. Why? Well, because our indeterminate form started out as something like 0 over 0, but then through a process of L'Hopital's rule measuring, it turned out that they both became finite, they both became non-zero at the same time. So when I took my derivatives here, the numerator became non-zero and the denominator became non-zero at the same time. So because this limit was finite, first of all, and non-zero, it means that the orders, the speeds at which these two sequences approach 0 are equal. So in other words, they're crossing the finish line at the same time, that this race is a tie. And if the race is a tie, in other words, if the sequence 1 over 2 to the n plus 1 is getting to 0 at the same speed as 1 over 2 to the n does, what does that tell you about the series summation of 1 over 2 to the n plus 1? If the terms are going to 0 at the same rate as the convergent series, summation 1 over 2 to the n, that must mean that our series converges as well. Okay. If the orders were equal, then both of these series are going to be doing the same thing. And because the summation of 1 over 2 to the n converges, so does the summation of 1 over 2 to the n plus 1. In other words, both of these runners belong in the same spot on our order thermometer. They both belong to that convergent category of geometric series up there at the top. We cannot say what this series converges to, but we can say for sure that it converges based on this comparison of orders. So L'Hopital's rule can help us to do this. All we need to do is pick a series which seems like it's close enough to what we're working on, but not quite the same, and show that when I divide the terms of one of those series by the other, that limit is finite and non-zero. If that's the case, then those sequences approach 0 with the same speed, the same order, and if one of them converges, so does the other one. If one of them diverges, so does the other one. This is called in your book the limit comparison test. I call it L'Hopital's referee, because I like this picture.